He the science geek.
And Karina.
2, 3.
Have you ever wondered why we put salt on roads?
Or even why we use windshield wiper fluid.
Or even why we add salt when boiling pasta?
Well, do we have the answer for you?
It's because of colligative properties.
Oh. So you may be confused. What are colligative properties?
Colligative properties, noun, are properties of solutions that depend upon the ratio of the number of solute particles to the number of solvent molecules in a solution.
There are 4 colligative properties. That's right, count them. 1, 2, 3, 4. Vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure.
Okay. Vapor pressure is the pressure of a gas above a liquid.
When you add solute to a solvent, the solute particles prevent the solvent particles from evaporating. This lowers the amount of gas above the liquid, effectively lowering the vapor pressure.
It's like when you are in a crowded room trying to reach the exit and you keep bumping into people. Those people are the solute particles preventing you, the solvent, from escaping the room or the solution.
Something boils when the vapor pressure is equal to the atmospheric pressure.
Because of vapor pressure lowering, it takes a longer time for a solution to reach its boiling point than it takes the pure solvent to reach its boiling point. So the boiling point of a solution is higher than that of its solvent.
Adding salt to water when cooking pasta does not make it boil quicker. It does, however, make the pasta cook faster because the water is boiling at a higher temperature and it makes the pasta tasty.
The formula for boiling point elevation is delta T equals I kBm. This takes into account the molality, which is a measure of concentration and a change in temperature from the boiling point of a pure solvent to the boiling point of a solution. Kb is a constant and I is the Van 't Hoff factor.
I wonder how much higher water boils when there's a solute in it.
Hey, let's find out! Okay. So, here we have 3 pots of water, 11 teaspoons of sugar,
And 11 teaspoons of salt.
So we are going to pour our solutes into 500 milliliters of water.
And then we're going to mix. And once all or most of the solute has dissolved, we will turn on the stove. And we will turn it on to medium-high temperature. So this is in front. Or medium. Medium sounds better.
And now we can leave them to boil. All 3 pots of water boiling. We have regular, sugar, and salt, and we are going to test the temperatures of all of them.
According to calculations, the boiling point of the sugar solution should have risen 0.17 degrees Celsius, while the boiling point of the salt solution should have risen 1.99 degrees Celsius.
So out of our 3 solutions, which one boils at a higher temperature, Karina?
The salt water does.
The change in temperature is explained by the Van 't Hoff factor. This accounts for the fact that some solutes dissociate while others don't. Ionic solutes that dissociate have more moles of particles per mole of solute, which covalent solutes don't. For example, salt, NaCl, dissociates completely into Na plus and Cl minus, which is 2 moles of particles per 1 mole of solute, which means I equals 2. Sugar, or C12H22O11, is covalent and does not completely dissociate. So there is only 1 mole of particle per 1 mole of solute, so I equals 1.
When using the formula for boiling point elevation, the Van 't Hoff factor affects the magnitude of the change in temperature. A larger factor will make the change greater. Therefore, the salt which has a larger Van 't Hoff factor makes the boiling point elevate higher.
I'm sorry.
We might as well do something productive with this. Hey Sam.
What?
Why did the solution go to the psychiatrist?
I don't know why.
Because its freezing point was depressed. As more solute is added, the lower the vapor pressure gets, which means the solution has a lower freezing point than that of ice. And ice will form at a lower temperature. Freezing point decreases because the process of freezing involves the transition of molecules to crystal formation. The process of forming crystals is interrupted by the presence of solute particles. The solute particles lower the temperature at which the molecules can align those into a crystalline structure.
The formula of freezing point depression is the change in T equals I Kf M. M is molality and Kf is the freezing point constant. This takes into account the molality, which is a measure of concentration, and a change in temperature from the freezing point of a pure solvent to the freezing point of a solution. Kf is a constant, I is the Van 't Hoff factor.
We shall explore this phenomenon through this at-home experiment. Okay.
Imagine it's a hot summer's day, and you're sweating bullets, and you think to yourself, I really need to cool down. But you have nothing cold.
But don't you worry your pretty little head. You can easily create a tasty snack in the comfort of your own home. All you need are a few ingredients.
We have half a cup of milk, a tablespoon of sugar, and half a teaspoon of vanilla.
We also have 4 tablespoons of salt, 4 cups of crushed ice, 2 quart-sized Ziploc bags, and 1 gallon-sized Ziploc bag.
You might also want a towel or pair of gloves to keep your hand from freezing.
Now we put all of the ice cream ingredients in 1 small Ziploc bag.
The sugar.
That was the sugar, right? Not the salt.
Yep. And the vanilla. Now you want to squeeze as much air as possible out of the little bag. And then you double bag it to keep it from being punctured and getting salty ice cream. Because no one wants salty ice cream.
Now we are going to measure the temperature of the ice. 1.7. Now we add the ice to the Ziploc freezer bag.
Now we pour in the salt.
And remeasure the temperature.
It'll take a little while for the salt to decrease the freezing point or the temperature of this ice, so we might wait a little bit.
And it says negative 12.9.
So now we take the smaller Ziploc bags of the cream and put it in the ice.
Try to get as much air out as possible. Then all we do is shake. The salt is lowering the temperature of the ice in the larger bag, which in turn makes the milk freeze at a quicker pace, thus creating ice cream. Technically, it's ice milk, but either way, it's refreshing.
Depending on how cold or frozen you want your ice cream, you could take it out and it could be creamier, or it could be actual like ice cream and frozen completely.
Cause the players gonna play, and the haters gonna hate, baby. I'm just gonna shake it off, shake it off. Heartbreakers gonna break, and the fakers gonna fake, baby. I'm just gonna shake.
It's still pretty creamy, so we're gonna keep shaking. Nom nom nom. When a solvent but not its solute passes through a semi-permeable membrane via osmosis and the system is at equilibrium, the difference between the two pressures is osmotic pressure. Because the solute cannot pass through the membrane, the amount of solute in the two compartments can never be equal. However, the pressure exerted by the water level in the compartment containing the greater amount of solute will eventually oppose the influx of water. Thus, the water level will only rise to the point at which it exerts sufficient pressure enough to counterbalance the tendency of water flow across the membrane.
Osmotic pressure can be seen in a U-tube, which is a giant tube shaped as a U, hence the name.
Our deepest apologies. We are not responsible for any damages, such as bleeding ears, caused by our singing. Thank you.
High, higher than the water, you raise the boiling point. I need you to elevate delta T, a collegiate property. Doesn't matter what it is, molal, you elevate the point. The solute you control, but it needs the mole now. Going up, elevation depends on kVp and molal of the solute. So high, elevation. Vapor, pressure of water at surface is lowered. Maybe I can educate your mind. Explain all the colligatives, can't miss the Van Top. The goal is elevation, a mole of solute we need per kg of water. Now going up, elevation depends on kVp and molal of the solute. So high, elevation.